Hello everyone, and welcome to the XGSA FD tutorial video. In this video, we're going to step through the tutorial from XGSA FD. Here, we've already created our project and selected the XGSA FD module. The next step is to go to the project information and then describe what you would like to use as your reference information for the project. The next step is to select reference standards. In the tutorial documentation, they've selected the EN5522 for the touch and step voltage criteria. We'll just select those down the line for the other reference. However, users can change their reference to align with the standard that they follow regionally. Next, we need to select our frequency. Following the tutorial documentation, we're going to use the 50 Hz frequency, and this allows us to move to the next stage of characterizing the soil. Typically in real projects, you would use a multi-layer soil model and the soil resistivity analyzer to take measurements and determine an appropriate soil model. With the tutorial, we're simply going to use a 100 ohm meter uniform soil. Next, we need to import our model. So going to the import and export icon, we can now navigate to the DXF of the project file we want to import. Here, we're actually going to import this transmission line model with an adjacent pipeline. Here we can see each phase conductor and the overhead shield wires that we're going to import independently so that we can give them unique properties. So we've navigated or directed the software to the DXF. Next, we are going to import each layer as that's associated with each phase conductor. EO1 will be one of our phase conductors. We need to select our library that we want to reference for assigning the characteristics of that conductor. And we'll use the tutorial L2 line type. In the library system, you can see the specific information about each of the conductors that we're selecting. However, here we're just going to continue selecting the overhead line tutorial L2 for each of our phase conductors. Another thing to note as we select these phase conductors is that we can assign a specific tag to denote which phase conductor we are working with. Could be phase A, phase B, or phase C. For the tutorial, we're simply leaving the tag name as corresponding to the layer that it's imported from. Next, we need to import the overhead wires. We'll assign electrode 4. Note that each of the conductors that we've imported, or each of the phase conductors we've imported, has been assigned a specific electrode. We need to go to the lines, overhead lines characteristics, and here we'll now select the overhead or OH1 description. Applying that. Now we import the pipeline. This is under the VO1 layer. We'll assign electrode 6, or electrode 5 actually, for that conductor. And instead of going to the lines library, we're going to maintain this conductor library and go to the pipe type. Here we can see we have various options to characterize our pipeline, but we'll just use the pipeline description. And again, VO1 as our tag that aligns with the DXF's layers. And finally, we're going to import this layer 0 and assign it as a background, meaning that the lines and conductors in our DXF associated with layer 0 are going to be visually displayed on our model. However, they won't play a factor in how our analysis is performed. Here we've imported our conductors, and we can see we have a list of all of the conductors that come from that DXF. We can go to our draw icon, and this will bring up a visual display of our system model. Here we can see we have the entire model of the transmission line and the entire pipeline. Note this icon here is a reference to an insulated joint along our pipeline. So if I go to the conductor editor properties, and in the victim dropdown I can see that there is a impedance at the end of this conductor. That represents our insulating joint at the end of this pipeline. We are going to modify this transmission line and the pipeline. So selecting the pipeline, I can go to simulate the infinite length, and this helps us avoid end effects. So I'm applying a transverse impedance that's going to approximate the impedance as if this pipeline were continuing on infinitely. And we'll need to do that with the other side of our corridor as well. Again, this is to avoid end effects in your modeling software and your modeling scenarios. In a typical analysis, you will need to define the phase conductor's current and voltage. And for a tutorial, we are first going to examine a steady state analysis. Here, under the source dropdown, we can see that these phase conductors already have assigned their voltage and current, so we don't need to do that for the tutorial. But in your real-world projects, you'll need to assign these according to your transmission line's configuration, voltage levels, and expected current. Now that we have our transmission line in our model and our pipeline with infinitely long lengths at the endpoints, we can now compute and debug this model. Our analysis has completed, and we now have a new analysis tab here. We can also see that our additional impedances that we've added in the model are displayed in this central table. I do want to see the voltage potential that has been induced on our parallel pipeline. And we'll do that by going to our distributions group box. And in the tag filter, I recall the VO1 tag name is associated with our pipeline. And I'm going to select the type of potentials that I want to see, the real, imaginary, or the modulus values. And I also want to display the pipeline as it's consecutively connected. So I'll select that for my sorting mode and go to the View 1D display. And here we can see the voltage that's induced along the path of that pipeline. We can also see this in the View 2D mode as well. And there is an XGL view, which allows you a little more flexibility in your perspective and how this is displayed. We can also plot the current potentials for our pipeline. And we'll include the real and imaginary to match the tutorial documentation. Now, in the tutorial document, the next stage is to evaluate the faulted scenario. Here we are going to modify our current system model and get to the same place as we have in our tutorial documentation. Instead of importing from a DXF, we're just going to modify our transmission line here to make it a faulted scenario. First thing I want to do is modify my transmission line phase conductor. So EO1 is one of my phases, and I need to select all of this conductor, and I'm going to assign it with 14,000 amp fault current. This is current that's going through my corridor, not faulting at any of my structures, but is going to have an increased inductive effect on my pipeline. This 14,000 amp value is chosen to align with the tutorial documents. Next, we're going to take a look at our other phase conductors, and we'll just zero these values out. This isn't necessary, and actually in a normal faulted condition these phases will have normal load conditions. However, we do want to match the tutorial documentation, so we're going to modify the source current on each of these other phases to be 0. Another difference between the steady state portion of the tutorial document and the faulted state is our pipelines have arresters that are operated due to the magnitude of the induced voltage. So we are going to model that by going to our conductor editor of this pipeline, going to our victim dropdown, and we're going to modify the impedance at the endpoint of this conductor. So we'll remove this relatively large impedance, and we're going to modify our impedance at the end of my pipeline conductor at this point to represent an arrestor firing and operating, and the equivalent impedance or grounding system associated with that point. Next, I'm going to modify the right-hand side of our corridor, and on this portion we are going to assume that the arresters fire, and instead of a 10 ohm impedance for the grounding system at the arresters, we are going to change that to 5 ohms. Now we can see I have this corrected, where we have two transverse impedances, one representing the impedance of the system where my arrestor is firing to, and the other representing the infinite length of this pipeline. Our next stage is to run this calculation, so we're going to use the debug and compute. So our analysis has completed, and we can see this red indication showing that this plot that's represented here is one of our old plots that was ran before our faulted scenario was ran. We want to see what our voltage potential is of our pipeline. So again, we go to the distribution group box, select our potential, and make sure that we've only selected VO1, which represents our pipeline. Next, we'll make sure we've selected our consecutive ordering, and we'll use the View 1D display. And here we can see the voltage that is induced upon the pipeline in the faulted scenario. We can also take a look at our current that's been induced upon the pipeline. Thank you for viewing the XGS Lab XGSA FD tutorial video. Please, if you want more information, reach out to us with the information displayed.